Good afternoon, everyone. Let us start. Today we shall learn a new chapter, chapter 10, atmospheric pressure. So now I shall share my screen. So this is chapter 10. The name of this chapter is atmospheric circulation and weather systems. And today we shall discuss about atmospheric pressure, its vertical and horizontal distribution. So let us read. Here it is mentioned that air expands when heated and gets compressed when cooled. Okay, just like any other object, air also expands when heated and compressed when it is cooled down. Okay, so let us say this is surface of the earth, and here we have a parcel of air. So this is a parcel of air, and when this parcel of air is heated, okay, so its volume will be expanded. Its volume will be expanded. Okay, so in this way, its volume will be expanded, and so it will rise upwards. Alternatively, see here in the other case also, here this is a parcel of air. Okay, and when this parcel of air is cooled down, okay, so it will be contracted, it will be compressed, the volume will be compressed, that is will be contracted. That is the point mentioned here. When the air is heated, it expands and gets compressed when it is cooled, just like other objects. And because of this expansion and contraction or compression, it results in the atmospheric pressure. It results in the variation in the atmospheric pressure, and the result is that it causes the movement of the air from high pressure to low pressure, setting the air in motion. Because of this expansion and the contraction processes, it causes variation in the atmospheric pressure. Say, and in the areas where there is expansion, okay, when the air is heated and when there is expansion, you will find low pressure, and when there is compression or that is when the air is cooled down, there will be high pressure. And because of these pressure differences, air moves from high pressure to low pressure. So that is the point mentioned here. Okay, and you have already learned in the lower classes that air in the horizontal motion is known as wind. Air in the horizontal motion is known as wind. See this movement or this movement. Okay, all these are known as wind. But if it moves vertically, so for example, this is the surface. If the air moves vertically up and down, this is known as current. Okay, if the air moves vertically, that is known as current, and the horizontal movement is known as wind. Vertical movement is known as what? Current. Okay, this current. And see the vertical rising of air, moist air cools it down to form the clouds and brings precipitation. At the same time, it also distributes or redistributes our temperature also because of the movement of the wind. And when there is vertical movement of the wind, then there will be cloud formation. Just see here. In this case, say let us say here we have this the surface of the earth is heated by the sunlight. Okay, it is absorbed, and here because of the heated earth, the air here will be expanded. The air here will be expanded and will rise upwards. And when it rises upward, then there will be cloud formation and rainfall. Why? Because see here, let us say this is a parcel of air at the surface, and when it is heated, it becomes lighter and it will move upwards. And when it rises upwards, then there will be expansion of the volume. That is, the size of the parcel air will be expanded. The volume will be expanded in this way, and because of this expansion, the air itself will cool down. What we call it adiabatic cooling. Okay, and because of this adiabatic cooling, there will be cloud formation and there will be rainfall. So about this, we shall discuss in detail later on about the adiabatic heating and cooling. So this is just an introductory part. And so in this chapter, say we shall discuss about causes of pressure differences, forces that control the atmospheric circulation, turbulent pattern of wind, formation of air masses, and the disturbed weather when air masses interact with each other, and the phenomenon of violent tropical storms. That is the origin of the tropical cyclones. Okay. So for today, we shall discuss about the concept of the atmospheric pressure and its vertical and the horizontal distribution. So let us read. The air, has a weight. Okay, and you must know that the weight of a column of air contained in a unit area from the mean sea level to the top of the atmosphere is called the atmospheric pressure. Let me repeat. The weight of a column of air contained in a unit area from the mean sea level to the top of the atmosphere is called the atmospheric pressure. Let's see here. Let us say this is the land surface, and here we have the sea here. Let us say this is sea level. This is the sea level, and here this is the sea. Okay, and this is the land surface, and let us say this is the top of the atmosphere. This is the outer limit. Okay, outer limit or the top of the atmosphere. And let us say this is a column of air. This is a column of air from the sea level up to the top of the atmosphere. This is a column of air, maybe square 1 square meter, for example. Okay, and so the weight of the air from the sea level, from the sea level here up to the top of the atmosphere is known as atmospheric pressure. This is known as atmospheric pressure. Okay, so the weight of this column of air, so let us say this is the column of air from the sea level up to the top of the atmosphere, and the weight of this column of air from the sea level up to the top of the atmosphere is known as atmospheric pressure. Okay. Any question? Joy Prakash, are you there? Joy Prakash, any question? So if you don't have, then let us continue. The atmospheric pressure is expressed in unit of millibar. Okay, the atmospheric pressure is expressed in units of millibar. That is 1000 of a bar. And at the sea level, the average atmospheric pressure is 1013.2 millibar. At the sea level, the atmospheric pressure is 1013.2. Here, the atmospheric pressure is 1013.2 millibar. Okay, here at the sea level, the weight of the atmosphere or the pressure of the atmosphere is 1013.2 millibar, and due to gravity, the air at the surface is denser and hence higher pressure. Just see here, this is the surface and we have gravity here, and due to gravity, the air here near the surface is denser as compared to here. Okay, as compared to here it is rarefied, let us say. This is because of gravity. Because of gravity, the air near the surface is denser than the air at the higher places. And you know that pressure is generally measured with the help of an instrument known as a mercury barometer or aneroid barometer. And here the mercury barometer, where nowadays we are mainly using 14's barometer. Okay, 14's name of the inventor. Okay, 14's barometer. So atmospheric pressure can be measured using these instruments, 14's barometer or aneroid barometer. See, I will show the photograph. So this is a picture showing 14's barometer. Okay, so this is very accurate one. And aneroid barometer is here. Aneroid barometer is here. Okay, the circular one. And here we have another picture also there. This is also an aneroid barometer. Okay, so these instruments are used to measure the atmospheric pressure, and you must know that pressure decreases with height. Pressure, if you move upwards, pressure will be decreases. Okay, just like temperature in the troposphere. And at any elevation, it varies from place to place. That means pressure can be varied from one place to another place. Okay, and which causes the movement of the air. And now let us discuss about vertical variation of pressure. Just now we have learned that if we move upward, pressure decreases. Okay, and so in the lower atmosphere, the pressure decreases rapidly. In the lower atmosphere here, near the surface, the decrease is very rapid. Okay, the decrease in height is very rapid. And here, the rate of decrease is about 1 millibar for every 10 meter. So if you move upward for about 10 meter, then pressure will be decreased by 1 millibar. Very rapid. Okay, if you just move upward 10 meter towards the sky, then pressure will be decreased by 1 millibar. And but it is not uniform. Okay, throughout the atmosphere, it does not always decrease at the same rate. And this table number 10.1 gives the average pressure and temperature at selected levels of elevation for standard atmosphere. Just see here, at the sea level, the atmospheric pressure is 1013.25. Temperature is 15.2 degrees Celsius. And if you move upwards for about 1 kilometer from the sea level, you will get the pressure of 898.76. Temperature will be 8.7 degrees Celsius. If you move upward for about 5 kilometer, pressure will be 540.48 millibar. Temperature would be 17 minus 17.3. Then if you move upwards for about 10 kilometer, pressure will be 265 millibar, and the temperature would be minus 49.7. So in this way, the decrease in the pressure is not uniform. It is very rapid near the surface, and it is gradual if you move upwards. And if we represent it in the form of a graph, then it looks like this. It looks like this. See here. Here the red line shows the decrease of pressure, atmospheric pressure. Okay. If you see the graph, it is very, very rapid, up to 10 kilometers from the surface. Okay. Then again gradual. Just see this one. This one. So this shows this line represents the decrease or the vertical variation in the pressure. And here this is troposphere. This layer is troposphere, and here we have the stratosphere. Here this is stratosphere, this is troposphere, and here within the troposphere the rate of decrease is very, very rapid. Here just see the graph here, it is going like this, and after that this gradual. Any question? Okay, let us continue. The vertical pressure gradient force is much larger than of the horizontal pressure gradient. Say for example, here horizontal pressure gradient means here we have low pressure, here we have high pressure, and let us say here the pressure is let us say 800. Okay, 800 millibar, and here the pressure is let us say 850 millibar. So here the pressure gradient means the difference between this area and this area is only 50 millibar. And the vertical pressure gradient means here this is the surface, and the pressure difference here the surface and here. So it is very, very large, as we see here. Just very, very large here. We have learned that for every 10 meter of ascent, pressure will be differ by 1 millibar. Okay, so it is very, very great. But this vertical pressure gradient means differences is generally balanced by the nearly equal opposite gravitation force. So on the one hand we have the pressure gradient, that means pressure decreases upwards, but this decrease in the pressure will be balanced by the gravity here. Okay, so let me just show you. Let us say this is the surface. So on the one hand we have this vertical pressure gradient. Okay, vertical pressure gradient is here, and on the other side here we have gravity, and this vertical pressure gradient here is equally balanced by the gravity, and that is why we don't feel the vertical movement of the air. See here, hence we do not experience strong upward winds. Next we have this horizontal distribution of pressure. Small differences in pressure are highly significant in terms of wind direction and velocity. If there is small difference in the pressure, then there will be movement of the air, and that is very, very important. Okay, and here on the map, horizontal distribution of pressure is studied drawing isobars. Okay, at the constant levels. So these lines are known as isobars. What are isobars? Then isobars are lines connecting places having equal pressure. So isobars are the lines connecting places having equal pressure. So this is an isobar, and its value is 1018 millibar. So the pressure here at the place A, then here at the place B, and here at the place C remains the same. Okay, and this is known as isobar. So here in this diagram, generally these low pressure areas are shown by these by a circular isobar here. So this is a low pressure area. Here we have got a circular isobar. So here it may be say 2 or 3 circular isobars may be there, but for the low pressure system at the center you will get the low pressure value. Here in this case the pressure value is 1014, and the next we have 1016, and the next we have 1018. So in the case of low pressure system you will find lower values of this pressure at the center. And in case of high pressure areas here, it is also represented by a circular or concentric isobars, but in case of high pressure there will be higher pressure value at the center. See here the pressure value is 1020 millibar, then next we have 1018 millibar, next we have 1016 millibar. Okay, so pressure gradient is towards this. In this case, the pressure gradient is towards the center. And these values, see here, these symbol, okay, like this or like this. So these are the symbols used in the meteorological maps to represent the speed of the wind. Okay, so here so it means this has a higher wind speed than this one. Okay, so it is expressed in terms of knot. Okay, so let us continue. In order to eliminate the effect of altitude on the pressure, it is measured at any station after being reduced to the sea level. So we have learned that see at the top of the mountain here we have this lower pressure as compared to the low-lying areas. Here the density of the air is high as compared to the top of the mountain. That means presently due to the differences in the landforms, okay, there will be differences in the pressure condition. And just to eliminate the effect of the altitude, okay, to eliminate the effects of altitude on the pressure, it is measured at any station after being reduced to the sea level. That means when we represent the pressure conditions on the world map, so all the recorded pressure conditions here, say for example here we have recorded pressure condition, here we have recorded for this station also, for this station also, but after recording all these values are reduced to the sea level pressure. Okay, all these places recorded here, recorded here, recorded here are reduced to the sea level pressure condition to eliminate the altitude on the pressure. And the sea level pressure distribution, okay, is shown on weather maps. Of course here this is the one. Okay, this is an example, and this is about the horizontal pressure distribution. Okay, let us continue. Now we have a world distribution of sea level pressure. So the world distribution of sea level pressure in January and July has been shown in figure number 10.2 and 10.3. And near the equator, the sea level pressure is low, and this area is known as equatorial low pressure. As I see here, this is the pressure condition in the month of January. That is, in this case, here The northern half, this northern half, that is northern hemisphere, is in the winter season, and here the southern hemisphere is in the summer season. And so here, as mentioned in the book, this is the equator here. Here, this is equator, and near the equator here, we find low pressure system. And this is known as equatorial. This is known as equatorial low pressure belt. Okay. Then along 30-degree north and a 30-degree south are found high pressure areas known as subtropical highs. So here, let us say here we have 30-degree north here. This is 30-degree north, let us say, and here this is 30-degree south. Let me write here 30-degree south. So along this line, you will find high pressure here. Okay, you will find high pressure here, roughly corresponds with 30-degree north and south. Here also high pressure here, high pressure here, high pressure here. And these high pressure systems or cells are known as subtropical highs. And further polewards along 60-degree north and the south, let us say this is 60-degree north, and here along this 60-degree north latitude, you will find a subpolar low. Here you will find a belt of low pressure system, and this is known as subpolar low. Likewise, here in the south also, okay, here along this line, you will find low pressure here, subpolar low. And beyond this, okay, here this is 90-degree north, that is the North Pole, and here at the North Pole you'll find high, okay, high pressure system. However, you must know that these pressure systems are theoretical. These are not permanent. Okay, it changes with the apparent movement of the sun. And likewise, this is the pressure condition in the month of July. So in the month of July also here, the northern half is in the summer season, and here the southern half is in the winter season. And see here in this case, here in the summer season, you will find low pressure. You will find low pressure over the continents and high pressure over the seas here. So this is Atlantic Ocean. This is Atlantic Ocean, and this is Pacific. This is Pacific Ocean, and over the ocean you will find high pressure, and over the land you will find low pressure in summer. And likewise, here in the winter, okay, the reverse may be there. See here over Australia, that is over the land surface, we find high pressure, okay. And but in other cases here, as compared to the land, you will find low pressure here also. In the Indian Ocean also low pressure also you will find here also. Just see here, this is the case of winter season, and here over the land we have high pressure, and over the oceans we have low pressure here. This is Atlantic Ocean, and this is Pacific Ocean, and this is North America, we have high pressure. So this is about the distribution of pressure in the month of January and July. And here we have some more maps here. This map also shows average sea level atmospheric pressure in January. Okay, and you may see the index also. Just see this index, and this represents this high pressure condition over 1024 millibar, And here in this January, in northern hemisphere, we find high pressure over the continent. Okay, very high conditions over the Asian continents. And again, here next we have the lighter blue one. So here the pressure condition is ranging between 1016 to 1024, and again it is also occupying the continental areas. Okay, and over the oceans, as I told you, we have low pressure here, low pressure here, and here this is continental part. But here, due to the cold current, see here we find high pressure also. And for the southern hemisphere, here, okay, this is in the summer condition. Okay, summer season, and over the land low pressure. Here in Africa also low pressure, low pressure. Over the ocean high pressure, high pressure, high pressure. And the values are here in the polar region. Okay, 60 degrees south, here the pressure condition is under 1000 millibar here, under 1000 millibar. And again in the polar area you will find high pressure. So this is for the January. Likewise we have for July. Okay, so for July also I think you'll find the reverse. And just see here, uh, in this case, here we have summer. Okay, we have summer here, and here we have winter in the southern hemisphere. And in the summer over the continents here you'll find low pressure because of the this heat of the sun. So here the pressure condition is under 1000, under 1000 millibar. And again it is surrounded by another low pressure condition that is ranging between 1000 to 1008 here over Africa also, including India. Then over the oceans, here in summer we find high pressure over Atlantic Ocean, then Pacific Ocean also there. This is equatorial region. And in the southern hemisphere here we find this high pressure over the these continents here, high pressure. And here this is what we call subpolar low. This is subpolar low. And here the low pressure is under 1000. And this is what, this is polar high. And here the pressure is more than 1024 millibar. Okay, so this is about the horizontal distribution of pressure. Do you have any question? Okay, if you don't have, then let us stop here for today. Thank you very much.